one and all who is present over here in the webinar series on this basic construction of instrument transformer. Today we have with us Mr. G.V. Akre sir. Let me introduce himself. Right now he is an engineer from electrical background and he is having more than 50 years of experience in manufacturing of EHV grade instrument transformer up to 400 kV. He is also a promoter and director of High Volt Trans Electrical Limited, which was established in 1985 in Halol, Gujarat. He is also successfully designed and manufactured 400 kV DC isolation transformers required in nuclear science research lab, which was the first time in India. He is associated with the Society of Power Engineers, Vadodara, for last 18 years and at present he is the chairman of this society. He is also former chairman of Instrument Transformer Division of IEMA, that is Indian Electricals and Electronics Manufacturers Association. He was actively associated with all academic bodies and was chairman of Board of Studies in Electrical Engineering Diploma Program of Nirma University, Gandhinagar. During last 15 years, he is instrumental in organizing several number of seminars and conference in IEMA and SP. So without wasting much of time, I would like to hand over this session to Sri Ghanshyam Akre sir. Sir, you can start now. Thank you.
Yeah, thank you, Professor Yadav sir. Good morning, everybody, all my student friends and the academicians. I am very pleased to be with you today and sharing my views on the instrument transformers. So we have got about 30 to 40 minutes and I will have to make it briefly. First the principles and then the construction of the instrument transformers. Friends, you are aware that all the electricity system which is existing in our country and elsewhere, a lot of energy is being transmitted from low voltage of 240 volts or even less to 760 kV or 1100 kV. And this energy which we receive in Gujarat particularly, it is received from the substations inside the city at 66 kV level. Before that it is 222 kV, before that it is 400 kV and 765 kV. So all these systems at different high voltages and large amount of the currents are actually flowing to us. Now, whenever there is a system like that, we need to have two things. One is the measurement of the energy which is being transmitted and which is being traded. And second is the protection of the complete system. So these two most vital things, and for that you require to have these sensors. That 765 kV, you cannot sense it by any instrument here. We have to reduce that 765 kV or 400 kV or 220 kV to very low measurable voltage. As per standard, it is 110 volt. Similarly, the very high currents which are flowing in thousands of the amperes, they also have to be reduced to a measurable limit, and that is 1 ampere or 5 ampere. So these sensors or this transmission or this transformation from the high voltage to low voltage and the high current to low currents are done by the instrument transformers. So these transformers, you can understand, have to be very, very accurate. That is one thing. Secondly, it should have the full life of 25-30 years and capable of protecting everything. Their quality has to be such that they themselves do not fail, because being transformer, being filled with the oil and subjected to the environment, they can fail. But then the quality of these instrument or transformers particularly has to be very, very high. So friends, now I will straightway come to the principle of this. Now, what is the current transformer? Current and potential transformers are defined as transformers intended to supply measuring instruments, meters, relays, and other protection equipments. They transform line current and the voltage to suitable standard lower values and also isolate the equipments connected to them from high voltage system. From this schematic diagram, you can see there is a current transformer at left side and a potential transformer at right. In the left side, we see the current in the transmission line is only tapped by a few number of the turns across the core, and the secondary is wound. This secondary gives the lower current. The transformation ratio of primary to secondary has to be such that you can get the low current. At the right side schematic, you can see it is the voltage transformer or the potential transformer. Here the winding of the transformer or the core is completely connected across the power supply. That means if it is 400 kV, all 400 kV will appear against that winding. So unlike current transformer, only the line is coming from high voltage and taking few turns and then going back. So it is trapping the primary current. While on VT, the full voltage is consumed across the winding of the primary. And the secondary turns are such that it reduces the voltage to the desired value. Now there are different current transformers. There is a core. This is the primary. These are the secondaries and the secondary load. Similarly, this current transformer can be a multiple secondary. That means one transformer is having one secondary, second transformer is having secondary, and both these transformer cores are looped through one common primary. So this is also possible. That means one common primary and there are two numbers of the secondary cores here, but they can be more. They can be more. I will tell you and explain you afterwards that why you require more number of the secondaries across this. In practice, actually the core which is you have seen as a rectangular, they are not rectangular cores in current transformer, but they are actually toroidal shape, round. I will explain you why that is so in future. Here you see the two windings, toroidal cores, having a secondary windings, one S1, one S2, and two S1, two S2. And there is a common primary from P1 to P2 having two turns in this thing. So this transformer is a wound core primary. This can have either single ratio, that means P1, P2 and S1, S2. That means if it is 100 by 1 ampere, it can have only 100 by 1 ampere. So single ratio transformer. Others can have a tap transformer. Here you see it can be 1 S1, 1 S2 will be 50 by 1 ampere, while S1 and S3 can have 100 by 1 ampere if there are double the turns. So like that, in the same one core, you can have two different current ratios. Similarly, in the same transformer setup with common primary, here I have shown you the two secondaries, one S1 and one S2, and two S1 and two S2. They are two different secondary cores isolated from each other. So they can be also having its own ratio. It is not necessary that all of these secondaries will have same ratio. The beauty of this type of the design is that your 1S1, 1S2 can be 100 by 1 ampere, or 2S1, 2S2 can be 200 by 1 ampere. For special type of the purposes, many times you require a cores, multiple cores to be connected to the loads and the protection gears at different ratios. We'll come to a principle of operation of this principle. You can see here it is a popular schematic winding drawing. Here the primary is shown as IP, secondary is shown as IS. It is connected with VA burden. In current transformer, the load is actually called its burden. Unlike power transformer and distribution transformer, where it is load in kVA, MVA. So here the load is very low. So it is called a burden. Now here, this is the important principle of the transformer. Here see that primary is shown as number of NP multiplied by IP. That means primary ampere and turns. So totally primary ampere turns is to be balanced by the secondary. Secondary it is shown as NS into IS. So depending upon NP and NS, you can have secondary currents. For example, if it is 100 by 1 ampere and I have got primary of 1 ton, then secondary will have 100 tons, so that both these currents will go according to our design, that is 100 by 1 ampere. Now, this is the case of the ideal transformer. Here, when you connect a meter or a protection relay, which is having very low resistance, and that is called as a VA, so current will start flowing in the secondary. And the drop across the relay or meter will act as the voltage. This voltage is developed across the secondary. Current is constant 1 ampere. So suppose if there is a 5 ohms relay which is producing the 5 ohms of the impedance, then 5 ohms multiplied by secondary current, that is 1 ampere, the VA burden will be 5 VA, 5 volt ampere. So this is how it is calculated. If this is connected at the larger one, then accordingly the VA burden will increase. Now, what are the significances of all this burden and voltage across the secondary? You see, any transformer as a function, it always have a primary winding, secondary winding, and the magnetic core. The primary windings is connected in this case to the primary current, so it is giving you primary ampere turns, and the secondary ampere turns are depending upon the number of turns as I have explained. So in ideal transformer, if you are passing 100 amperes, your secondary will always have exactly 1 ampere. There is no error in the ratio. But in actual fact, it does not happen. What happens is that when you are giving the primary current, the core, the magnetic circuit itself will draw its own excitation current, which is required for magnetizing, which is required for overcoming the eddy currents and the watt losses in the magnetic core. You have learned that while designing voltage transformer, distribution transformer and everything. So when it draws the secondary current, along with the secondary, it is drawing also the magnetizing current. But before that, I will show you this formula, which is the well-known formula. That is, any voltage across the secondary or any winding is equal to 4.44 multiplied by frequency, multiplied by flux density, multiplied by core area, and the number of the turns. So on that basis, you can see the flux density will be equal to VA divided by IS by 4.44 F core area and turns. This will give you the flux density. The significance of the flux density is there, which I will explain you further. You see, in actual current transformer, what happens now? In ideal transformer, number of turns in primary into the current flowing in it will be balanced by number of turns in secondary and the secondary current. So this is the ideal cases where the ratio error will not be there. But in practice, due to excitation current, IE, CT equation is changed to primary ampere turn, that is NP into IP, and that will be equal to secondary ampere turn, that is NS into IS, that is the external current which you are driving, and the internally it will also draw in addition to that NS multiplied by IE. That IE is the magnetizing current drawn by the core. Now the scenario is changed. You can see it is not balanced exactly as an ideal transformer. Here the error has been introduced by NS into IE because it is the extra current it is drawing. For example, if it is 100 by 1 ampere, then because of the excitation current, the primary will be possibly 101 ampere and the secondary will be 1 ampere. Because that 1 ampere in the primary is drawn by the core to maintain the flux and errors and losses of the core. So that means your ratio error now the ratio becomes 101 to 1 ampere, not 100 by 1. So that is how the error is very important. Why the errors are important? In current transformer, if we are dropping the voltages, for a simple example of 66 kV to 110 volt, the ratio will be 600. Similarly, if you are connecting it to the current transformers of 100 by 1, the ratio will be 100. So if all these two meters, that is voltmeter and voltage coil and the current coil, are connected to the measurement meter, then their multiplying factor will be 100 multiplied by 600. So 60,000. So here in this case, the error in the secondary measurement will amplify to 60,000 times. And that is why the accuracy of this current transformer has to be very, very high. And this is how it is actually recognized. What are the effect of the voltage developed across secondary due to VA, that is volt ampere burden? Here that voltage will produce flux density, and flux density will draw the excitation current, and that is how we can have the errors in the transformers. But in the general transformer principle, you see, in case of the current transformer of protection system, the high voltages are developed across the secondaries because the relay has to have the high voltages proportional to the fault current. Fault current may be 20 times. So it is the 20 times the voltage it will take. And that is why here also you can see by this principle, this is the BH curve, or the voltage across the excitation current. Here the voltage, I have shown it here at about 900 volts, the current which is drawn, and at 1000 volts, the current which is drawn. So the knee point voltage of any transformer indicates this magnetizing characteristic. So it gets saturated, starts saturated at a point which, when raised by 10%, it will produce the 50% more current. So that is how the definition of the knee point voltage. So better this transformer, it should have a less current or the less magnetizing current for the high voltage across that. I have told you that these cores of these current transformers are not rectangular type which we have seen. It is round or toroidal fashion. Why toroidal? You see, the excitation current which is drawn by any magnetic circuit will be utilized for flowing the magnetic flux inside the core. You have seen in the power transformers or distribution transformer laminations, they are actually set one by one. That means there are air gaps appearing at the joint. So every lamination will have their joints, and many joints will be there. There will be air gap, and this air gap is resistive. This will not allow the flux to pass very easily. So that means its reluctance will be more. So in that case, what happens? If you use rectangular type which are having the air gaps, then it will draw very high magnetizing current, and that will produce very high value of the errors, which is not required. Hence, particularly for our current transformers, the cores must be having, or the magnetic circuit must have the gapless system. That means it should not have any gap. And that is why these toroids are made out of the long strip of CRGO, and they are wound, annealed, processed, and then they are presented. In that case, what happens, whatever the current it draws, that is a magnetizing current which draws, it will be strictly by the property of that material of the core. And it is not in addition to that the impurities like air gap and other things. So that is why the current transformers are always, you will find, in the toroidal fashion. This is the shape, the toroid with secondary winding. And the secondary winding number of the turns can be varied depend upon the ratio. The two major differences between the measuring and protection. As I told you, the main purposes of the current transformer is, one is the measurement of the energy or power, and second is the protection for the total system. So major differences is the accuracy classes and the safety factor. In current transformer of metering type, it needs high accuracy at load currents, while protection need not have the high accuracy. See, protection is utilized for sensing if there is a fault. If there is a fault, when there is a fault, current will flow or this in the system more than 2 times, 3 times, 4 times, or even 20 times. So there is no measurement at that length. Only relay will understand that it has drawn a much more higher current than it's rated for, and that is why it is subjected to fault, so it should act. And that is why the accuracy is not very important in the protection class 6. In safety, the safety factor in the metering city should have lesser value so that it saturates before the meter can get damaged due to the passage of fault current. I have told you that when fault current flows, primary will carry that fault current. It will not be restricted. But secondary in protection class should faithfully produce the secondary reflected current. That means if it is 20 times, then secondary in place of 1 ampere should carry 20 amperes, so that the relays and the relay system will understand fast the severity of the fault and they will act fast or slow. While in case of the current transformer, for the metering purposes, you will see if 20 times current flows as up, during the fault, then the meter may get burned, because 20 amperes it is not rated for. The meters are delicate and they may burn, they may get damaged, or their accuracy will go. So in that case, the metering should be inherently made in such a way that it will not faithfully reproduce the primary current in the secondary. That means it should saturate. So generally when you are passing 20 times current in the primary, secondary should have 2 or 3 amperes maximum, so that meter will not get damaged. And that is why the core of the metering class will be always having area less, so that when the current flows more than 3 times, 4 times, or 5 times, the core will saturate and it will not increase the secondary current beyond certain level, and it will protect the meters. So that is why the terms can be that instrument security factor has come inside the city. So it is generally 5. JETCO wants always 5. 5 means when the current in the primary increases 5 times, the secondary should not carry 5 amperes but less than that. By formula or by the definition, it should not be more than 4.5 amperes. So this comes 4.5, that means your saturation has now started. So if instead of 5, if the current is increased to 10, it is not going to carry 9 amperes. It will be saturated and it will be carrying possibly 5, 6 amperes depending upon the characteristic of the core. Then that is how the current will be limited in the secondary circuit, that is meters and relays, and they will be protected. Similarly, for reducing the magnetizing current, as a special core material is used, such as nickel iron and nanocrystalline. I have told you that toroidal cores and the CRGO material will draw the excitation current or magnetizing current, and that will produce the error. Now, nowadays we require to produce 0.2 S class of the current transformer for tariff metering in Gujarat or throughout India. So this 0.2 S class as per IEC indicates that your error should not be more than 0.2%. This is very, very delicate, and that's why the normal CRGO, that is grain oriented cold rolled iron, may not give that type of the low current, and that is why a nickel iron core or nanocrystalline core are nowadays used. They are very, very costly, maybe about 10 times costlier than the CRGO, but as a special purpose, they are being used today. Protection city, as I told you, that it should have the high safety factor. That means it should allow the secondary current to increase faithfully in proportional to the primary current for protection system. And that is why, this core is having a high cross-sectional area, because the core should not get saturated it should allow the flux density, and it must have the high cross section. So it is larger size, while metering core is smaller in the size. Now, what are the precautions? This is the normal principle, because there are construction part also we have to see. So I am going fast. If you have got some difficulties in understanding, you can ask me during the question answer session. Now, city, after you make the secondary, primary and all this thing, it requires a particular precautions also. You know that cities are connected across the meter or relay. If suppose the meter gets open circuited, what will happen? Everybody knows and heard that there will be very high voltages developed across the secondary. That is because if I have given the example 100 by 1, primary is 1 ampere and the secondary is 100 amperes. So long the secondary is shorted through the load, it will carry only 1 ampere, and there is voltage developed across this according to VA burden or the proportion to the load. But if it is open circuited, what happens? It becomes a sort of a transformer, power transformer, distribution transformer, having 1 turn in the primary and 100 turns in the secondary. So if whatever the voltage drop is there in the primary, 1 volt, 2 volt or 5 volt, that will be amplified by 100 times, and secondary will appear at very high voltage. So depending upon the transformer, dangerously high voltages are developed across the secondary, and that can give the shock to the operators, or it can damage the transformer, and it can saturate permanently the core also. So thereby the full transformer can become useless. Now let us come to CT and PT. What is the difference between the CT and PT? You see in the example in the schematic, current transformer, the supply line is only tapped with a few number of the turns in current transformer, while the supply in the supply side of the full voltage is dropped across the potential transformer, as you see in the right side. So this is a basic difference actually. Here, the primary and secondary will have the isolation depending upon the voltage class. Suppose if I take the 66 kV, then there will be always insulation between primary and secondary, which will withstand 66 kV. It is not simply as you see on the diagram. I will now next for the type of the current transformers. What type of the current transformers are there in the system today? Construction point of view, you can see it is a hairpin time or dead tank design. We will see the details and you will understand them what they are. Then second is the eye-bolt design, that is also coming into the dead tank variety. And the top core design, they are the live tank design. Depending upon the insulation, there are different. One is the oil impregnated, oil paper impregnated. These are the insulation. Another insulation can be epoxy. Now another example can be of the SF6 gas, which is used in circuit breakers very, very widely here. And now in India also, the SF6 type of the current transformers are already in the market and being utilized. They are very safe. Then fourth is the optical CT, where the isolation between the high voltage and low voltage is perfect, and there is no question of any high voltage failure in this case. So let us go for the details of this. I already explained. The instruments are connected at every stage of the protection of the system as well as for the measurement of the energy. They are required to be the most reliable equipment from operational point of view. The reliability of the total power system depends upon the quality of this equipment. The main insulation, that is isolation between the primary and secondary of this equipment, is most important factor, and it is designed taking into consideration the operating voltage, over voltages appearing in the electrical network due to its exposure to the atmospheric condition, and also due to the switching of the equipments in the system. Here, this is the important part, why the different tests are actually conducted, taking into care the effect of all these over voltages coming. When the transformer system or the transmission system is exposed to the atmosphere, it is likely to have the lightning stroke coming across that, which is having a very, very high voltage. It is very impulsive voltages. Similarly, it can have the overloads because of some feeders are drawing high currents because of their usage and all these things. So they are within 2 to 3 times maximum. But there will be the switching surges coming in this when this is the inductive and capacitive circuit whole system. If you consider, then if any equipment is switched on or switched off, it produces the surges. And these surges, these impulses from the lightning stroke and these over voltages which are coming across can damage the equipments connected to it. Hence, the insulation is done selecting all sort of thing, and only after that the insulation is designed. I will just give an example for this insulation, why it is so important. Suppose if you have got 66 kV, then the insulation between primary and secondary has to be 66 kV. That is for operating voltage, 66 kV face to face, and city primary to earth will be 66 divided by root 3. So 38.1 kV is its continuously operating voltage, plus minus 10%. But it is tested at 140 kV for 1 minute. That is to take care that the insulation is designed in such way that it will withstand a 140 kV, nearly 3.5 times higher than its operating voltage for 1 minute, so that its insulation property is assured. Similarly, the same transformer is subjected to impulse also, and this impulse is generally done in the laboratories like CPRI or the ERDA, and many people are having their own impulse generator in their workshop also. Particularly for power transformer, it has become a routine test. So impulse voltage test has to be also conducted. And that is why the insulation is done in such a way that it will pass or it will accept all the stresses produced because of these different disturbances, voltages appearing in the instrument section, in the transmission section. We'll just have the differences. What is the dead tank type city and what is the live tank city? You can see the dead tank city. I will show the first figure here. These cores are actually at the bottom level. They are bottom level, that means they are in the tanks which is connected to earth, and that is why it is called a dead tank design. Okay. Now the primary is very high voltage from the top, example of say 66 kV. Then this primary will come to the bottom, that is on the ground potential, and it will take loop across the secondary as a primary winding and go. Now what do you see here? That primary is at very high voltage, while the secondary is at zero potential or the earth potential. So in that case, your primary has to be insulated. You cannot only simply insulate the core, because there is a tank and so many things are there we are near to. So the primary which is coming at bottom, that has to be insulated fully. So one difference is there in this dead tank type of the design. The primary is insulated and secondary is not that insulated. It is 3 kV or 4 kV system voltage only. And as I explained you, that this is the principle that leads are actually taken down in bolt or hairpin type, and they are insulated for the high voltage. Here you can see the actual insulation system. Here this is the hairpin design, and you can see that this is P1 and P2, and this is a primary either copper tube or aluminum tube, and it is insulated from top to bottom with this insulation. That is the main insulation part you see. It is fully insulated. So primary here is insulated, and then the cores are actually inserted at the bottom. Then it is assembled in the grounded tank. Then there is the insulator to separate from ground to the primary high voltage, and it is a tank at top, and then this transformer is dried and full with the oil. So this is one of the hairpin type design generally occupies this. If you go for the live tank design, and what happens in the live tank is this. Here you see the primary is at top. This is P1 and it has taken few turns across the core and then does. And the core also is at top. Now this core is through these leads connected to the secondary leads, secondary terminals, which is at earth potential. That means the core here is at earth potential, while the primary here is a line potential. So essentially here you have to insulate the cores and secondary, and that is why you see the cores are insulated and then they are inserted here, and the primary is only looped through it. So this is called live tank because the cores which are lying, they are in the tank which is live at high potential, and that is why live. Principle of operation, that is magnetic circuit and the primary to secondary, is same in all the cases, but construction point of view they are different. You can see the cross section of this live tank job. We'll go shift to the secondary winding now. It is now we have started slowly to the construction point of view. So individually we have seen the primary and secondary insulation between them. The insulation part will go in depth again, but secondary winding we'll see. What is the secondary winding? Have the qualified for. More than one secondary core can be used, that I have already shown you. Each secondary can have a different current by selecting different turns, that is 100 by 1 or 100 by 5 ampere. Even secondary amperes also can be different in the different cores. So one transformer or one current transformer can have one single primary but have the 5 to 6 number of the secondary cores which will be feeding to the different class of the equipment. For the protection, they will be supplying to the different class of the protection, differential, balance, overload, and all sort of things, and they will be having a different characteristic, while they will also have 1 or 2 cores for metering and tariff metering and for the measurement of total system. So that is how the secondaries are actually not one only, it can be having 2. Similarly, the secondary can have tappings, as I shown you earlier, that is 100 by 1 ampere will also have the tapping of 150 by 1 ampere. Similarly, things is report that same common primary and heavy tap secondary. These are the 2 separate cores on the common primary. This is how it will look in a toroidal core. The primary is having this loop together and the cores are different with the secondary connection different. The winding of the transformer, here you will see the core material with the high permeability used, which takes at low excitation. I have explained that core has to be very low excitation current, and hence the material like metal like nickel, iron and mu metal is used, so that current transformer can be classified as in 0.2 or 0.2 S for the accurate measurement of energy. You can see the primary winding. Here it can be a bar primary, it can be a hairpin type as I shown you, or it can be a live tank which is having a wound primary. But the selection of the primary is also very important here, because the instrument transformer, the primary has to carry operating current but also has to carry the short circuit current. An example I can just give you. The current transformer is rated for 100 by 1 ampere. Okay, and its short circuit current rating is 40 kiloamperes for 3 seconds. That is what the JETCO is acquiring today. So you can say the same transformer, even 100 amperes, which is low current, we need to provide the cross-sectional area of the primary in such a way that it will withstand 40 kiloamperes for 3 seconds also. And for IC and IS, this current densities are also specified for taking care of the short circuit current. That means if it is 3-second rating, its current density should be 105 per square millimeter or less, and for 1-second rating, it can be 180 mm. Just one example, just to give you the idea how the difference is between this. Suppose I have selected one ratio of 150/1 and STC has 40 kilo by 1 second. In that case, what happens? Cross section for 150 by ampere will be 150 amperes divided by 1.65 amps per mm square, because this is normally working at a low current density. So this will require 91 mm square of the section of the primary. But if we see the second case, that it also has to suffice the 40 kiloampere for 1 second. In that case, 40 kiloamperes divided by 180 amps per mm square, which can be safely taken by that, it will produce 223 millimeter square. So you see the same transformer, because of its dual rating, instead of 91, we have to utilize 223 mm square. Otherwise, the transformer may burn during the short circuit currents flowing through it, fault current flowing through this. Also, the heat which is generated during the STC, that short circuit heat is generally not dissipated. It is 1 second or 3-second rating. Then the full primary is insulated by the paper insulation. So in that case, there is no possibility of any dissipation. Hence, the total primary takes that heat and as a latent heat, and the temperature of this winding can be instantaneously increased very high, causing the burning of the insulation surface. And that is why the formula which I have shown you, that is very important. Also, the primary should withstand the short circuit dynamic current also. So when you are in the current like 40,000 amperes are passing for 1 or 3 seconds, the number of turns, they will have a mechanical forces develop across that, and that can damage the transformer. So generally, the peak current, which is responsible for developing the mechanical forces, is 2.5 times its RMS. So RMS value is 40 kiloamperes. So naturally, its peak value or the dynamic value will be 100 kiloamperes. That will produce very, very high mechanical forces. And if the transformer is not designed or the primaries are not properly reinforced, they will fly off or they will damage. This is a sort of winding it is done. You can see the open circuit. Here you can see the cores which is wound and the secondary leads are taken out. And these primary in form of the strips, they are wound across that. Now you see, it is not only a simple winding. This each and every turns is reinforced. In such a fashion that if the short circuit forces are passing through that, then even 100 kiloamperes say, then mechanical forces will not collapse this winding and will avoid the short circuit between the turns or anything. So that is how the primary has to be designed and done properly. The shape of the transformer, that is a bolt type which I have shown here. Now, this when it will be assembled and ready for the insulation, it will occupy this type of the shape. You see, the primary which was there in the rectangular sections is now completely rounded off. And the leads are also taken out in the round tube, because if insulation is provided on the rectangular strip, it will create the sharp corners at high voltage and they will fail, because sharp corners will always produce the partial discharges in the area, in the region which is occupied by the insulation. Hence, this technology of the high voltage insulation is very specific, and you have to adopt this principle of rounding. Here the insulation, it is not only simply by winding the paper, but this paper is also divided into section of the capacitances, or that is called a grading, capacitive grading of the insulation. This is the subject which is in the high voltage, and I will not take much of this time on this inspection, but then insulation has to be very, very proper, and that is normally done in the high voltage cases by providing the capacitors. I will give the example of that in short, how this insulation is completed. You see, this is the section of the primary winding. This primary is at high voltage, and this is the section of the core which is connected to the earth potential. Now, how this is insulated? This can be insulated by a single paper layers, say 25-30 millimeter for 66 kV, and that also can insulate it. And they can be insulated by inserting these metal foils in between, so that each metal foil with respect to this primary will have its capacitances, and this will act as a capacitor dividers. So the voltage across each capacitor is kept in such a way that they equally divided. Otherwise, what happens if you do not put these capacitors? Then the insulation which is very near to this primary, which is having lesser diameter than the earth potential here at the top. So this insulation, suppose I will say a 5 millimeter section of the paper here will be having a gradient, voltage gradient of nearly 130 to 150 volts per mil. So this will be sharing, this paper will be sharing this voltage in such a way that the bottom, that the first one will have very high stress of 150, while the insulation, same insulation which is at the higher level, that is at the higher diameter, may have only 80 to 90 volts per mil. So you can see the difference between these two. Same paper is sharing at 80 volts and 150 volts. So that is not economically used, optimally used. And that is why these voltages are actually divided into small fractions, and they are made to divide the voltage across all the sections and all the elements of the insulation. So that is how you can reduce the diameter of the primary insulation, and you can make. This is how the current transformer is generally done. This is primary. This insulation is capacitively graded, and then you put the core here, tank, insulator, and top chamber for P1, P2, and it makes a transformer. Professor Girish, am I taking more time?
No, sir. Actually, we should stop as per the time constraint. So we should have this 5 minutes for question answer session right now.
So where do you want me to? Where do you want me to stop? Where do you want me to stop? You give me 5 minutes. 5 minutes.
Okay.
Okay. This is how the insulation insulated hairpin primary looks like this. And after assembly, this is the current transformer. Here, this is a dead tank core where all these cores are mounted. The primary is coming from P1 to P2 at bottom, and then is going as a return conductor, that is P2, P1, P2. And there is an insulation or the insulator between the earth potential and the top potential. This is essential because the transformer is actually lying in the atmosphere. There will be rains and all this thing, and that is why this part of the insulation is different from the internal part of the insulation. Internal part of insulation we have seen, but the external also it has to be insulated properly. The long life of the transformer is also important, because you see these are the hermetically sealed transformer. Its life has to be 20 to 25 years. There is no chance of changing the oil or filtration of the oil and drying it if it catches the moisture. So that is why its life, once you install, then for 25 to 20 years, it should work without any problem. Otherwise, if they fail disastrously, because they generally explode like a bomb. and they explode themselves. At the same time, they damage the surrounding equipment also. And that is why this transformer has to be hermetically sealed by using different method. That is a nitrogen cushion. It means the oil in the transformer is not allowed to come in contact with the atmospheric by any leakage or anything. And that is why they are isolated by using nitrogen cushion, nitrogen being inert gas, and the stainless steel bellows also. So this is the most effective method today. Many tests are conducted as per the requirement of the insulation. And the VT also they have explained, but it is the same thing. There is not much of the difference except for the construction of this VT. You see the primary and there are two secondaries. Is the primaries having more number of the turns while the secondaries are less number of the turns. This primary will appear actually, in fact, is a fine gauge wire, maybe 30-35 gauge, and it will having thousands of the number of the turns which will be connected across primary. General cross section is like what you see, and this is the shape of the transformer of VT. If you see at the bottom, it is a core winding, insulated properly, and again taken up at top. This is 220 kV, and this is a cross section of the VT. So I think, friends, I will stop here for the construction. So let this question answer will be there, so that I think I can clear more doubts on their mind. So Professor Jadavji, you please take it.
Okay, sir. Thank you very much, sir. So I think, is there any questions from any audience point of view? So far as this basic construction of instrument transformers are concerned. Or otherwise, you can mail your questions to me so that I will hand over to sir and we will get feedback from him and I will again feedback to you. So at least today, whatever the session I have, for that, I am thankful to you, sir, for this esteemed words delivered towards this basic construction of instrument transformers, which found to be very interesting one. Moreover, I would like to have the whatever the session we have obtained from this particular session. So it will very benefit to our students and some faculty members as well. So that for that again, I would like to express my sincere thanks to you, sir, for giving the excellent coverage over this basic construction of instrument and transformer that includes CT and PT. So at the last, I would like to thanks again and acknowledge our gratitude to group for exposing and exploring this field of this IT. So thank you very much, and we expect that you should again come to for our such kind of sessions in future also.
Surely, I'll promise. And thank you very much for actually inviting me to deliver this lecture. I also invite your students and academy in batches to visit our factory also. Of course, once they have come, you can see the actual construction going on your factory.
Definitely.
And you are aware that we are also strong members of Society of Power Engineers. And they are having a lot of programs in Gujarat.
Correct.
Parul also on 18th, they are going to be joint programs between Parul and ourselves. So on my behalf, please request the students community to join as the members of the SP, and they can attend many programs of SP, which will give them the engineering knowledge and all this. So thank you very much, Jadavji.
Thank you, sir. Thank you very much.
Bye.